I first met Alessandro when I moved to Aachen for my bachelor's thesis, where we shared an office. And in that time, Alessandro was actually working on his PhD with David DiVincenzo. Since when he's been doing a lot of really interesting and very practice-oriented theory work, very creative work in our area. So yeah, I mean, he's been doing work on supermagnetic qubits and doing work on Hamiltonian quantum computing, as well as GKP error correction, which is also one of my favorite intersections. And so today he's going to talk about error mitigation and quantum-assisted simulation in the error-corrected regime. Yeah, so.
Okay, yeah, thanks, Jonathan. So first of all, I would like to thank the group for having me, and hopefully, I mean, I will also visit next year. So today I'm going to talk about my recent work, which was a collaboration with Matteo Rostaglio that was mainly developed when we were both at QTech at TU Delft. And the work is about error mitigation and quantum-assisted simulation in the error-corrected regime. And in a sense, it started because we were both looking for, let's say, we were both getting into quasi-probability representations of quantum mechanics, and this was somehow the origin of this work. Okay, so let me first start by giving a brief recap of what's actually the recipe for a quantum circuit to be hard to simulate for a classical computer. And we will see later why this connects to my work. So first of all, when we are taught about quantum information, the first thing we are said is that we are told is that what we need to have a hard quantum circuit. So the reason why it's hard, it's because we have a big Hilbert space that grows exponentially. Then we think maybe about it for a few moments, and we immediately realize that for sure we also need entanglement. But then when we study even more quantum information, we realize that entanglement per se is also not sufficient, because we learn about a theorem that is the Gottesman-Hill theorem that I will also mention a bit in the next slide, that tells us that in principle we can generate all the amount of entanglement we want, but if our quantum circuit is restricted to work with stabilizer states, that can still be classically simulated. So we also need what in qubit quantum computation is known as magic, that is somehow a deviation from the stabilizer formalism. And in a sense, all these three features, so big Hilbert space, entanglement, and magic, are in a sense necessary condition for a quantum circuit to be hard to simulate for a classical computer, but they're necessary but still insufficient, because one can still come up with some problems that apparently are hard to simulate, but in reality they have a let's say a classical algorithm. Anyway, so this is for qubit quantum computation. In continuous variable quantum computation, or in qubits quantum computation with the odd dimensional, what is actually magic is known as non-Gaussianity. Okay, so what we want to accomplish.
As a remark, I mean, you rightfully emphasized necessary condition many times, and for good reason, right? In that, I mean, that's all true what you say, but I mean, we painfully know that like to what extent we need structure in quantum algorithms, and that has been known since the early work of Shaw on hidden subgroup problems. But even like in quantum machine learning or newer approaches, we are getting painfully aware of how much structure we need to hope for anything. So yes, that's all right what you say, but I mean that these increases alone will not make an interesting setting as such. But of course, you emphasize it yourself.
Yes,
yeah. Thank you.
Okay. Okay, so what we want to accomplish in this talk, so it's, let's say, it's quite a limited, let's say, goal, that is to try to analyze within the same framework some quasi-probability based methods. And in particular, we will consider what I call the error-corrected regime of quantum computation with a certain definition that I will give. And in this unified framework, what we want to try to generalize are essentially classical simulations based on quasi-probability methods, quantum-assisted classical simulation when we have some quantum resources, and what I will call error mitigation. In a sense, this unified framework will try to see all these cases as particular cases given the amount of quantum resources we have. Okay, so as I mentioned before, let's say all these quasi-probability based methods, in a sense, will be limited by the amount of magic that is present in the quantum computation, meaning that it's the amount of magic, or as we will see, the T count, that will make it hard to simulate. But anyway, so I mentioned before the Gottesman-Hill theorem, that here a brief recap. So if we have a quantum computation that starts from the zero state on n qubits, and we apply adaptive Clifford circuit, meaning that we can also condition the Clifford operation that we do on the outcome of a Pauli measurement. And in the end, we measure, indeed, at the end of the circuit, a Pauli operator that I here denote as P. This is classically simulable by the Gottesman-Hill theorem, and there are actually many ways of seeing this. And the most common one is to use the tableau representation of stabilizer states that is efficient because it's essentially an n times 2n binary matrix. So in order to achieve universality, we need to add some magic, meaning we need to add the magic states that I here denote as T, and this is an ideal magic state. And the reason why we can achieve universality by injecting magic states via this so-called state injection gadget is that we can realize a so-called T-gate that is essentially this diagonal gate. And we know from Nielsen Chuang that Clifford's plus T-gate is universal. So I was saying that, as you know, Clifford plus T-gate is universal for quantum computation. So as I said, using the stabilizer formalism, we can simulate Clifford circuits, or in general, stabilizer circuits. But in principle, we can still use the formalism to simulate general quantum circuits at the price of an overhead. And there are several proposals for doing this. And what we consider in this talk is this idea by Howard and Campbell in 2017. And the idea is quite simple. So they introduced this concept of robustness of magic. And the idea is that the robustness of magic associated with a T-qubit state whose density matrix I will denote as rho T. So T denotes the number of qubits on which this density matrix acts. So we look for the compositions of the state here in terms of the stabilizers, meaning in terms of the projectors associated with the stabilizers. And one can show that this decomposition, first of all, it exists, obviously, and the coefficients here, the Qx, are real and normalized to 1. So this is immediate to see. And the robustness of magic is the minimum negativity associated with this decomposition. That is the sum of the absolute values of the weights. Actually, once we have any such decomposition, not even the optimal one, one can come up with an algorithm to simulate the output, or better, to obtain the average observable on the output of a quantum computer. So in general, we will be interested in decomposing T states, obviously. Some immediate facts about the robustness of magic that will also be related to the quantity we will introduce in a bit. So first of all, it's a quantity that is larger than 1 with a quality holding if and only if rho T is a mixed stabilizer state. So this is a rather obvious property. It's submultiplicative, meaning that if I have a product state, I can just look for the composition of one of the states and one part of the state and the other part of the state. This makes a completely valid decomposition, but it's not the optimal one. As I will remark, actually, this submultiplicative property at a certain point is, let's say, one can hope to get better decompositions that have smaller negativity, but at a certain point with the system size, this property is kind of lost. Obviously also determining the robustness of magic is an unscalable convex optimization problem, simply because the number of stabilizer states grows super exponentially. And so eventually one is always limited to decomposing few states on few number of qubits if one wants to look really for the optimal value. So this means that we will always use block decompositions of few qubit states. Okay, so what is actually the algorithm once we have such a decomposition? It's quite easy, and it's reminiscent of what one does when there is a sign problem in Monte Carlo algorithms, and this is a general feature of quasi-probability decomposition. So what one does is simply we sample from the absolute value of the decomposition, meaning that we take the absolute value, we renormalize it, and this is a probability distribution. Now we essentially sampled a stabilizer state that in this, so here we will have as input a stabilizer state. So we can simulate it with the Gottesman theorem. And the output is the output of the measurement, of the simulated measurement, times the negativity, times the sign of the weight. So one can show that this is an unbiased estimator. So if we repeat this many times and we take the arithmetic average, we actually have the result of the ideal quantum computation with one problem, that is the fact that this estimator is multiplied by the negativity. And since the negativity must square exponentially with the number of T gates, its variance will grow exponentially. And one can show using a common formula that is often inequality, that the number of samples that one has to draw is essentially proportional to the negativity squared. And so it must scale exponentially. And so this is where the hardness in simulating circuits that have some magic comes from in this kind of simulations. Yes.
Could I ask a question?
Yes.
So I think I misunderstood something, but why do we need to sample, and why can't we just kind of simulate every SX?
Yes, so the point is we want to simulate, so we want to decompose this T gate, T states, that are what are making the simulation hard, and they are not stabilizer states. So you look for a decomposition of these T states in terms of stabilizers. So once you sample, you can run the stabilizer simulation efficiently on a quantum computer. Now the overhead will come from the fact that you have to draw many samples.
So, but, and it's not possible to just kind of just simulate all stabilizers that have some component, and then like then use like these probabilities to reconstruct afterwards.
Yeah, this is somehow what the algorithm does. So so you say you just sample all possibilities, and then you kind of as a post processing you assign some weight.
Yes,
But
exactly.
I don't know if that.
Yeah,
Well,
I mean,
well, actually, you have a problem of the fact, in a sense, here we are using an important sampling. The fact that some weights are higher than the others, and in that case, you would still need to simulate an exponential number of stabilizer circuits, right?
I see. Yeah. Okay. Just some numbers.
Yes, that's indeed, that's a good point. But there is still this exponential overhead will be there.
Yeah, I see.
Yeah, in a sense, this is maybe maybe this is similar to what you propose. Is similar to the approach of the stabilizer rank simulators, I guess, where there what is limiting is the number of terms in the decomposition, I would say.
Okay. Yeah.
But I mentioned that the hope of, I mean, this like randomized approach has a hope that like the total number of iterations that you need to go through is less than the stabilizer rank of the.
Yeah. I see.
Is this always true, or is this?
So comment. So these kind of techniques are worse than the stabilizer rank techniques, and will actually. So this is, I will give it as an outlook on how to generalize what I'm going to show to stabilize. It's known that this is not the optimal way.
So by worse, you mean you need more samples than the stabilizer rank?
No, the stabilizer rank works actually differently. You don't. I mean, to estimate the average, you don't you don't really draw samples. You actually. I mean, there is also an algorithm to actually reproduce the output of a quantum computer completely, meaning you reproduce the complete statistics.
Right.
But that is not the dual of what I'm trying to do here, of this. So, but yeah, stabilizer rank simulators are different, but they perform better than this technique. The thing is that it's
no,
not.
I mean,
yes.
Okay. No, I think what I meant by stabilizer rank is it's not really concretely the stabilizer rank thing that exists, but it's just so you do this decomposition that is in the box into stabilizer states, right? And you just count, okay, how many terms are there, right? Like, and one thing that you can do is instead of taking a subset, which you do when you sample, of all of these linear components, is you just take all of them, right? That's what Peter Yan was suggesting. And so if you just take all of them, you would end up with an exact simulation, but that would like. So the question was just like how the like number of measurements, or how the number of iterations that you got from the Swiftings inequality, how that sort of compares with the total number of terms in these kind of decompositions.
Yes. Okay, that's a good question. Although, okay, maybe we can come to that. So I know on top of my head the number of samples you have to draw will scale as 1.6 to the T count. Yes, and I think that actually in the decomposition, if you decompose each T state into stabilizer states for one qubit, I actually think you have two terms. And so I think that should maybe show that this is better than doing that. I'm not sure. Yeah, but indeed that's a good point. Yeah. Yes. Yes. So yeah, 1.6 is smaller than 2. Yeah. Okay. Okay, but so another comment is that somehow this is very similar to also what is done in when simulating the output of continuous variable systems when one uses the Wigner function. So there, the limiting factor is the Wigner negativity. Here, it's a different kind of negativity in this kind of approach.
But it would be, I mean, all you say has an immediate translation to that world, right? I mean, even like actually the one of the first papers we wrote on the setting where the Wigner function is like all positive all the way through.
Yes, yes.
And that where the operations have positive Wigner function in the sense that their Troyer-Minkowski isomorphisms are positive.
Yes.
We even wrote it like one by one in the sense there's one formalism for both sides so that you can interpret the symbols to be either like discrete Wigner functions for prime dimension, like on the one hand, or
yes,
observable ones on the other hand. That was like the same notation even made it all through the entire thing.
Exactly.
It's slightly different for this negativity quantified in L1 norm or 1 norm settings, but other than that, it's extremely similar, right?
Yes, it's extremely similar. Yeah, I mean, eventually what changes is the frame. So here you're using stabilizer frame. So okay, let's say this is for qubits. So obviously for qubits we have everything is a bit more. It's a bit trickier, but
complicated on the Wigner function side. Yeah, sure.
Yeah. So in you can do the same. You can introduce a robustness of magics for qubits with the odd dimensional, and essentially what changes is the frame, meaning that with the Wigner function you use the phase space point operators, and here you use the stabilizer states. You would use the stabilizer states. So it's the frame of your decomposition.
Yeah.
Yeah. Okay. Okay. Let's move on. The previous technique was a classical technique to attempt to simulate a quantum, the average of on the output of a quantum computer. But recently, and with recently actually mean 2017, so a very similar technique was introduced in this paper by IBM people. I call quasi-probability-based quantum error mitigation. So this is together with many error mitigation techniques that have been introduced lately. And the idea of this technique is quite similar, but now it uses a noisy quantum circuit to simulate the output of an ideal quantum circuit. So the setup is the following. So we have our ideal quantum circuit. So here we consider directly circuit model without not the magic state model. So we have some unitaries. The cursive symbol denotes the quantum operation associated with the unitary. And we want to measure an observable at the end. So this is the ideal circuit, but practically we have a noisy quantum computer in which what we can implement is some noisy versions of these unitaries here. But the point is that if we know the form of these quantum operations, we can now look for the compositions of the ideal unitaries in unitary quantum operations in terms of the noisy ones. And one can show that this is again a quasi-probability distribution, meaning that it's positive and normalized to 1 if these are a completely positive trace preserved.
So to be sure, so what you're doing is like it's a random unitary channel. You are basically mixing unitaries. Is that right?
I'm actually mixing. I'm quasi-mixing quantum operations.
I see. Oh no, okay, fine. Like okay, quasi-mixing, but still, it's like a if you want a super operator picture that you are
exactly. So O alpha are not unitaries.
Oh yeah, wonderful. Yeah.
Good. O alpha. So the hope of this approach is that obviously this sort of decompositions exists. Because I mean, if you can only do the completely polarizing channel, obviously you can hope to do it. But yeah, so in general, given what you can do on a noisy quantum computer, these decompositions actually do exist, because you have still quite a good C0 or
do they always? I mean,
some
this
other
totally
gates.
depends on the O's you have, right? I mean, if you have
Yes, yes.
like if you do very weird stuff and every like gate that you try to build is conjugated by some amplitude damping or something like that, then
yes, but in that case, if you have that model and you can do universal gates, this decomposition exists.
that still exists. Oh,
yes,
okay.
yes,
Cool.
it does. Yeah, I mean, in a sense, it's I mean, from what I've seen, it's difficult that a quasi-probability decomposition of this kind does not exist, actually.
Oh.
I mean, if you have sufficient freedom, yeah. Anyway, so the idea is that to each of these decompositions, we have associated a negativity. Of course, we would like to try to minimize it. And now if we decompose each of these unitaries, we have a negativity for each of them, and the total negativity is the product of the single negativities, which shows also that if you use this approach of decomposing each gate, eventually the total negativity will also have to scale exponentially with the number of gates that you're actually doing. So again, the technique that is called an error mitigation technique is exactly now the same as before, meaning we sample from the absolute value. We now run the noisy quantum circuit. We extract the information. So we extract the value of the measurement, which for the purpose of this talk, of course, let's assume that at least that is ideal. And again, one uses often inequalities and sees that the number of samples we have to draw scales like the negativity squared. So if the negativity is 1, this is the number of samples you need an error delta with probability 1 minus epsilon. And this would be the ideal quantum case where this quantity is 1. So as you see, this is a general framework of quasi-probability methods. I mean, once you have a quasi-probability decomposition and you have a way to run each term of the decomposition, you can always use the same algorithm. This is the message.
I don't really understand what's going on. So
yes,
somehow you are kind of decomposing the quantum circuit you want to perform into implementable quantum operations.
Yes.
But then I don't understand, I guess, what the error mitigation algorithm is.
Yes, the error mitigation algorithm ensures that I can construct an unbiased estimator for the observable at the price of having its variance to be increased, and so I have an additional overhead.
But the upshot is it's an unbiased estimator. So like with unbounded number of samples, you will get the right outcome. But the whole question is a question of the sample complexity, right? So that for a given number of settings, what can you say?
Yes.
Good.
Yes.
So what is the sum over next total negativity?
I'm sorry.
This product, I mean, of K is 1 to L.
Yes. So each decomposition will have a negativity.
Okay.
And if you decompose each of them, you're basically finding a total decomposition. So this would be a block decomposition, as I will call. And the negativity is simply the product of all of them. Yes, in the most general case, it's the product of all of them. Yes, but so this is to say that the previous, what we saw before, that was using stabilizer states to construct a classical algorithm. Now it's the same idea, but now we are using a noisy quantum computer to construct an algorithm that can run on the noisy quantum computer to simulate the ideal quantum computation.
Okay.
Still at the price, the overhead will still be here, and will always be so no free lunch from this point of view. Okay, so this was just mainly still motivation. And so what is our setup? So what are we actually assuming? So we want to construct a general framework for these techniques. And so we make some typical assumptions of what is known as magic state distillations. That's to say, we assume that we have our quantum information is already encoded in some quantum error correcting code that has that guarantees that stabilizer operations can be made fault tolerant. So we can do Clifford's, Pauli measurements, and preparation of stabilizer states, and classical randomness that is actually redundant now. We can do them fault tolerantly, and at the beginning we will assume that they are completely ideal. Now we have available noisy magic states that without loss of generality we assume they are of this depolarizing form. So I denote by tau the ideal magic state projector, so the density matrix, and tau delta is a noisy magic state with error delta, considering the polarizing noise. Key thing is that we show that if you want to bring the let's say the noisy magic state into the depolarizing form, you have to apply twirling, and that makes always things worse for our discussion. Okay, so but what's the idea is that essentially we are considering our quantum computer in an intermediate error corrected regime where these operations are available and ideal, and importantly, these are the operations that the Cotes-Manil theorem allows us to simulate classically. And so in this framework, we can see that how the addition of noisy magic states will allow us to, in a sense, also boost the classical simulations of the quantum computer, of the ideal quantum computation, in which way, as we will see, by reducing the negativity, as we will see. Okay, so now I introduce this concept of what we call the Qrom, quantum-assisted robustness of magic, that formalizes the idea of robustness of an ideal quantum computational resource, ρT. So ρT is again a state that is acting on T qubits. Relative fewer noisier available ones that I denote as sigma r. So sigma r is an r qubit state with r smaller than T, smaller or equal, and yes, so sigma r acts on r qubits. Okay, I denote by qt of sigma r the set of all T qubit states that we can reach starting from sigma r stabilizer operations. And why do I do so? Because stabilizer operations, I'm assuming them that my quantum computer can do them ideally. So ideally, I can reach all these states. It's possible to achieve all these states. Important thing, obviously, Qt includes all the T qubit stabilizer states, because I can simply do Pauli measurements and then I apply Clifford, so I can create all stabilizer states. So all the states that are used by the Cotes-Manil theorem, that are the stabilizer states, are included in my set. So at this point, the idea is very natural, I would say. So we define the quantum-assisted robustness of magic as the minimum negativity of the decomposition associated with of the composition of ρT associated with all the possible states that are reachable by stabilizer operations acting on sigma r. And so the robustness of magic is the minimum such negativity. Is this clear, or I went a bit too? Did I go too fast on this?
I think it's clear.
Okay, good. I think the idea is very cool. And okay, so Again, now, as I said before, we in all the talk and in the paper, we focused on decomposition of the T gates, of the T states. And we consider that we have fewer noisy magic states than available. So this is these are the kind of decompositions we are probability-based algorithm is the same. So sample from the absolute value, use now our particular version of a noisy quantum computer, where the noise comes mostly from the T gates, sampling overhead, negativity squared, and it's minimized by the Qrom. Something that is valid for the robustness of magic, so the classical version, and the quantum assisted robustness of magic, is that also the quantum assisted robustness of magic, to solve the convex optimization problem is an unscalable, it's an impossible problem that becomes hard, very, very hard, even for 2 qubits. And in fact, we only found for 2 qubits suboptimal decompositions. Okay, some properties. Again, these are quite intuitive, similar to the robustness of magic. So it's faithful, meaning that it is, okay, it's larger than 1 with equality holding if and only if rho T is in the set of available states. It's submultiplicative, meaning that I can, so here I say it maybe in words, it's easier than going through this formula. We can, if we have like a 4 qubit state that is a product state, I can simply decompose 2 qubit at a time, and that's a completely valid decomposition. It's simply suboptimal, but it simplifies the convex optimization problem. So we will always focus on few qubits decomposition, and if we have many qubits to decompose, we will use a certain amount of time that decomposition till we decompose all of them. It's monotonic with respect to stabilizer operations in the following sense. This is also quite intuitive. If you apply a stabilizer operations to the ideal state you want to decompose, essentially what you can do is you can make it noisier, and so the negativity will decrease. If you now instead apply a generic stabilizer operation to the resource state, you can make it noisier, so it's worse, so the negativity will actually increase. Just a remark, if the stabilizer operation is a Clifford instead, this holds with equality. Okay, it recovers the robustness of magic in the sense that if sigma R is a mixture of stabilizer states, then the Qrom is equal to the Rom. This is also quite an intuitive property, and it must recover it because we have the stabilizer states in our set. Okay, so now we will continue analyzing these block decompositions of few magic states in terms of few noisy magic states. And we consider, first of all, what we call the error mitigation case, in which R is equal to T. So we don't have
wait. That was the last thing that you showed on the last slide, like very briefly before you clicked over.
This.
For the next slide. No, the previous one.
Yes.
If it's a mixture of stabilizer states, of course, that's right. But I mean, you really mean mixture, not linear combination.
Mixed. Yes, mixed.
That's crucial because otherwise it would be ridiculous.
Yeah, okay. So you say it's improper to say mixed. If I say mixed,
no,
it's
very fast. Okay.
Okay. Yes, it's mixed.
Very good. Yeah, I'm with you.
Mixture. Okay, so I call error mitigation case R equal T, simply because this is the most similar situation to what one has in the, let's say, the error mitigation technique when we have noisy T gates, because we don't have actually a limit there of the amount of gates we can do. So here we can potentially make a noisy version of our gate for any gate. So R equal T is what I call error mitigation. So single qubit case can be, so now I look at for a decomposition of a single T state in terms of one noisy T state. So the optimal decomposition can be found analytically. Well, we confirmed it numerically, obviously, but it simply uses this resolution of the identity where DZ is the completely, sorry, it's the dephasing channel. And it has the following form. So below a certain error threshold, which I think many of you can guess which one it is, the robustness goes as the Qrom goes as 1 divided 1 minus delta, which shows that for small delta it actually scales linearly. And above this threshold, the square root of 2, and it recovers the robustness of magic. And simply because the threshold is the point where the state, the noisy magic state, is entering the stabilizer octahedron, that is the convex Hall of the stabilizer states for 1 qubits. And so obviously we are always interested in the case where we are outside of the stabilizer octahedron. And the polygon, the shaded polygon that you see is represents the convex Hall of all the states that we can reach via stabilizer operations, meaning Cliffords, in this case, starting from the state tau delta. So you see that it's an increased, let's say it includes the octahedron, but it's still a nicely looking polygon. Another comment is that the optimal decomposition simply uses tau delta and Z applied to tau delta, and it has this representation, meaning that tau delta is the state here, and Z applied to tau delta is just the state on the opposite side, of the polygon. So this is the single qubit case, but we know that we have this submultiplicative property, meaning that if we now try to decompose a 2-qubit T state in terms of 2-qubit noisy T states or 3 to 3, we should hope for better decompositions. Now I will show this, but first one comment is that we obtained, so we asked ourselves the question that how can one bound the fact that, can one see the fact that one expects still this Qrom to scale exponentially with the T count, and indeed we found such a bound, and I think it's quite interesting. So it's a lower bound that shows it has to scale exponentially, and the lower bound is here. So this is simply an upper bound that is given by any block decomposition in general, and the lower bound is expressed in terms of any convex magic monotone, meaning that it's not increasing under stabilizer operations, but this can be really literally any such magic monotone. It could have even not existed. This bound would hold with the point that problem that it doesn't exist, but it actually does exist. And most of all, there is one that was recently introduced in this paper, that is the dyadic negativity, which is multiplicative for single qubit product states, so product states of single qubit states, and it is kind of a generalization of the robustness of magic. But now we also allow in the decomposition to look for stabilizer dyads, meaning that the cat here can be a stabilizer, And this, the bra here can also be another stabilizer. And the dyadic negativity is the minimum. Now it's actually not really a negativity in the sense that this alpha J can be complex, but still it's the minimum sum of the absolute values. And since this can be computed analytically and for one qubit and it's multiplicative, we use this in this formula to actually show that indeed the bound, there is a lower bound that scales exponentially with the T count, and so also the Qrom has to scale has to grow exponentially. Okay, questions on this? Okay. So
what do you know about saturating this bound? Like, is it a special?
Yes, that's indeed a good question. Okay, so for one qubit, we know that this does not saturate the bound, although for one qubit, we found another bound that saturates, but that doesn't generalize to many qubits. And in general, I think I have the feeling that it's the optimal decomposition would be far from. I think it's the bound cannot be saturated actually, not when expressed with this dyadic negativity. I don't think it can be saturated. But this also shows that the bound shows that somehow if you take let's say it's a kind of negativity per state, that is simply you take this to the 1/t. For small delta, this scales linearly. So this is another. So if you take this to 1/t, which is a measure of a negativity per state, and so you compare it with this, that is the single qubit case. So this also scales linearly, but now there is a coefficient of 1/2 here, but it's still linear. So it also tells you that not only that it scales exponentially, but there will be this linear behavior. But I don't think this bound can be saturated. Okay, so now we look for multi-qubit decompositions, and I decompose two ideal magic states in terms of two noisy magic states and 3 to 3. And I compare and I take either the square root of I take 1 to the third, to the 1/3. And these are actually the best decompositions we found, which we managed to find analytically, but using Mathematica, so we don't have actually a way to generate them. And what we see when compared to the single qubit decomposition, so this is as a function of the noise delta, is that it's true that these decompositions, so I actually think this one is optimal. This one, we didn't have a proof that this is optimal, but I think it's the optimal one for
that's interesting. What makes you think that? That's an interesting intuition.
Because I included all the possible Cliffords, and I don't think one can get much more by. So you know what is left out is Pauli measurement on one part and apply all the Cliffords, and I have the feeling that cannot give you much. So all the Cliffords were included here.
Okay.
All the Cliffords and all the stabilizers were included. What was not included was allowing Pauli measurements on part of the circuit, and then, you know.
I understand.
Yeah, so I have the feeling this is actually the optimal one.
Thank you. That's great.
Well, this might not be the optimal one for free. Anyway, these are the best we found. So obviously we had to restrict the number of states to run the code. So what we see here is that it's true that these decompositions are better, but this seems to be true especially when delta is relatively large, which it might not be the interesting case to consider delta 0.2, which is quite high. While when delta gets smaller and smaller, this decomposition will get closer and closer to the single qubit one. And in a sense, it seems that this submultiplicative property gets kind of lost for small delta. Obviously, like any advantage in terms, any reduction in the negativity will be an exponential reduction in the number of samples. But for me, it doesn't seem to pay off to go to high decompositions, to block compositions that are too large.
Oh, could you repeat what delta was?
Delta is the error on the magic state, the polarizing error on the magic state.
Okay.
Yeah.
Thank you.
Yes, and this bound is the asymptotic one. This is the asymptotic one, meaning that this is 1 divided 1 minus delta half. Okay. Yeah, as you see also, this is the limit where you enter the stabilizer octahedron, it gets flat because you recover the robustness of magic.
I mean,
Okay.
just a very simple question. But when you can you use if you have, say, one T state on 2 qubits, can you use that to prepare T state on like the other qubit?
I'm sorry, I didn't understand.
No, I mean just like this magic monotone question. Like if you have one T state and you have 2 qubits, one of them is the T state. Like can you use it to implement something like a controlled Hadamard or so to prepare a T state on? No, but you need to measure.
What would you do except teleporting?
Yeah, exactly. What would you do?
Like there is no cloning theorem, so you can't do T and T.
No.
And you can only teleport.
Well, I mean, the no cloning theorem is for unknown states, right? I mean, but you know the states.
Yeah, but you can't map a T0 state to a TT state with a Clifford circuit, because it would be equivalent to just mapping 0 to T, which is non-Clifford.
Okay.
Okay. Yes, let's continue. Maybe I should speed up a bit. So, so far we assume that the Cliffords were completely ideal. Now we remove this assumption, and we consider that there is still some noise, residual noise on the Cliffords. And specifically, we take this very simplified error model for each 1 and 2 qubit Cliffords, meaning that with probability delta C, so delta C is now the error on the Clifford, we have the ideal Clifford, and with probability delta C, we have the completely depolarizing channel, meaning that this sends it to the identity on 1 or 2 qubits. So now we have the problem that this the state injection gadget also has errors. Again, we consider errors actually only on the C0 and on the S-gate. We also obtain what the channel is if we consider measurement errors, but it's not shown here. So the point is that if now you decompose the tau delta, the tau in terms of tau delta and considering noisy Cliffords, that's not enough to have a actual decomposition of the T gate, simply because you would also have errors on eventually your final goal is to decompose a T gate. And if everything is ideal, decomposing a T state is enough, is equivalent to decompose a T gate. But if you have error on the Cliffords, this is not equivalent. So at this point, eventually what we did is we obtain what's the quantum operation that one implements when we have a noisy T state here as input in the state injection gadget, and we have also noisy Cliffords, and it is this thing here, where D is the completely dephasing channel and G is the completely depolarizing channel. And at this point, we looked for a decomposition of the T gate in terms of the available quantum operations. So now we are decomposing the gate, not the state as before, because now we have also errors on the Clifford. The decomposition is relatively simple, meaning that it uses this channel here, meaning we just apply, we just inject tau delta and we use the noisy Cliffords. Z applied to the channel, and also the completely dephasing channel. So these are the terms that are in this optimal decomposition for one qubit optimal decomposition. And now the negativity of this decomposition has this form. So there is an additional term that comes from the error on the Cliffords. Obviously, when delta C is equal to 0, it recovers 1 divided 1 minus delta. That is the negativity below threshold of the single qubit cases with optimal Cliffords.
What is
Yeah.
Z here? Is it just a single qubit or not?
What?
Vgate? What is the Z here?
C.
The Z.
Z. Yes, Z is the Pauli Z. It's a Pauli Z.
Okay.
Yes.
So so you're decomposing the perfect T gate in these three terms, where the first one is like
exactly
the outcome of the circuit.
Yes.
Plus
yes.
C plus 2. Okay.
Yes. Okay, so now I decomposed. I took into account the fact that Cliffords can be noisy. In here, so in the state injection gadget as well, and then when we run we also have to take into account that in the Clifford operations in the quantum circuit will also be noisy, so we'll have to use a decomposition of the noisy Cliffords as well, but this was already worked out in the literature. So we will also decompose the Cliffords in terms of the ideal Cliffords in terms of the available noisy Cliffords. Okay, so before discussing the previous slide, basic thing of the idea of what magic state distillation does. So in magic state distillation, we have n noisy magic states with error delta initial. We apply stabilizer operations. We assume them to be ideal. And one obtains k smaller than n noisy magic states, but with smaller error. So the idea of magic state distillation is that if we do this many times, eventually we can bring the error. Down. So I say this because in the next slide we will try to let's say combine our idea with a magic state distillation protocol. And in particular, we consider this Braviha protocol. The Braviha protocol that is described in this takes as input 3k plus 8 noisy magic states and gives k noisy magic states with error that decreases quadratically. And in particular, we consider the case k equal to 2. So what do we do here? We consider noise on the Cliffords and on the T states. And we ask ourselves the following. So given a certain initial error on the noisy T state and on the Clifford, which we assume much smaller, of course, we say that we can tolerate an overhead, a sampling overhead in this example is 100, meaning I tolerate only 100 samples more than what I would need in an ideal quantum computation. So this is, of course, my choice. So I can only tolerate 100 samples more than the ideal one. And I ask myself the question, how many Cliffords and how many T-gates can I do? And after one round of distillation and 2 rounds of distillations, how many Cliffords and T-gate can I do? So if we start from delta 0.05, which is this area here, we see that eventually we are, while we can do many Cliffords, basically like 20,000 Cliffords like here, the number of T-gates you can do is very, very small. And it's like, with this overhead, you can do like 40 T-gates or something like that. To give a comparison, the best, let's say, stabilizer rank simulators claim that they can arrive at simulating like 200 T-gates, but not too much more than that. If we now apply one round of distillation, of course, we get better. And we can kind of simulate like something like 100 and something T-gates. And after 2 rounds of distillation, when the error will become something like 10 to the minus 3, which is actually a reasonable, starts to become a reasonable on a quantum computer, we see that we can simulate like, for instance, when we have 600 T-gates, we can simulate 60,000 Clifford gates. So this picture is mostly to give some order of magnitudes of how things will scale if we consider we limit the sampling overhead. If you want to let's say increase these numbers, you still have to do more and more rounds of magic stick distillation.
So just to be sure,
yes.
So by simulating, you mean simulating the ideal quantum circuit on
Exactly.
a noisy quantum computer,
exactly,
and not like classic. Okay, because
yes,
yeah, then I understood correctly.
Yes, correct.
Thanks.
And the nice thing of our framework is that you recover the disks when the delta is sufficiently large, actually. So there is as a special case, it is interpolating between the classical simulation and the ideal quantum computation. Okay, maybe I will actually skip this because this is simply, there is one thing on this slide is that we assume that the magic state distillation is ideal in this slide, but we also consider the case in which we mitigate possible errors even in the distillation routine, which is shown in this slide, but maybe if there are questions about it, let's continue because we are running out of time.
I have one question to
Yes.
that. If you could go back, so I mean, this is all like the setting is you fix the overhead and then you sort of see how far you can go.
Yes.
But are there also statements like how high this delta is allowed to be to, like, similar to a threshold theorem where you have sort of when your error rate or like your imperfection is below a certain number, then you are guaranteed to be, at least in principle, able to suppress it exponentially. Where like, because here it's sort of a computational thing where it's not
yes,
it's not about protecting the qubit, it's about.
Yes. My take on this is if the number of noisy states that you have is smaller or equal than the number of ideal states that you need, there is no such threshold, I would say. Then you need to consider, I mean, you need to consider a setup in which you have more states. That is what magic state distillation does.
Yeah, true. Okay. Yeah, but and
You can't. So if the number of, I think, I don't know if this is a completely general thing, but for sure for this kind of methods, no, you don't. If you have same number of T states as the number of ideal T states, there is no such threshold value that will tell you I would get better and better.
the more samples you take, that's kind of the
so it's continuously interpolating. So
okay, cool.
It's not
because obviously, like if delta would be 50%, obviously it wouldn't work because everything is just.
Yeah, so if delta is 50%, actually, it will be a mixture of stabilizer states. So it's the same as doing a classical simulation.
Yeah.
The threshold is 0.29, something like that.
Okay, good.
Yeah.
Thanks.
Okay, so now let me go quickly to what I call quantum-assisted simulation, when the number of qubits, available qubits is noisy magic states is smaller than T. So again, the goal is the same. So why do I call it quantum-assisted simulations? For two reasons. So first of all, it interpolates between the classical case when we don't have any magic state, any resource, and the error mitigation case where we have all the noisy resources we might need. In addition, so there are some results that show that in principle, if you have an adaptive Clifford circuit that takes as input the zero state and our magic states or our noisy magic states, one can compress the problem to an adaptive Clifford circuit that actually runs only on a R-qubit quantum computer. This is valid also, it was also valid before, but this means that you can always consider, so if you have a circuit that has R states and runs on n qubits, you can always convert it with a polynomial classical overhead to an adaptive Clifford circuit that is running on an R-qubit quantum computer. So this is results from these two papers here. So this is also this famous Bravi-Gosset paper. So in what follows, we will look for the compositions of the ideal magic states in terms of R noisy magic states where R is smaller than T. So in particular, we consider two cases. So when we have half the noisy magic states as those that would be needed, and one third. So here we compare. So before discussing the plot, we compare what the classical overhead. What is the scaling of the classical overhead? This is essentially the negativity squared. When we use the best known stabilizer decompositions that was done in this paper by Heinrich and Gross, and we compare it with the overhead that we would get when we have still a relatively noisy magic states, when we have half of the states that we will need and one third of the states that we will need. So as you see, especially in this case, like there is still quite a big advantage compared to the classical simulation, because you also see it here, where on the y-axis we have the T count, and on the x-axis we have the error delta, and the colors depict the ratio between the number of samples of the algorithm with T over R equal 2 and T over R equal 3, divided the samples that we will need classically using this decomposition with this overhead from this paper here. And you see that, like, for instance, when we have small noise here and we take T over R equal 2, already with 300 T gates, we have, of course, this is a property of the fact that everything is exponential. We have to take like something like 10 to the minus 27 less samples compared to the classical situation. So this shows that indeed the advantage, even if you have less noisy magic states, can be still quite a lot compared to a standard classical simulation. Okay, here I finish with an outlook. So actually, there are several ideas that can be, let's say, further analyzed starting from this paper. So first of all, I didn't consider the distillation case where the available states are larger than what would be needed. In addition, I envision that there could be something similar that can be done using the Wigner function, but now for when we consider qubits or continuous variable systems. And also, one could try to treat in a similar way stabilizer rank simulators that perform better, as I said at the beginning, than these quasi-probability-based simulators. But this, let's say, this generalization is not at all immediate because of the way these stabilizer rank simulators actually work. They work in a different way. So for a comment, there were 2 related works related to our work, to our paper. So there are these work from IBM people and ETH, and this Japanese group that is actually working on error mitigation. Okay, I went a bit long, but thank you for your attention.
Okay. So let's thank Alessandro for the talk, and if you want to clap, maybe you should unmute.
Clap, clap, clap. Wonderful, thanks for this exciting talk. That was pretty good.
Okay, cool, super. Thanks, Ali. So are there any questions? Alessandro,
Can you maybe elaborate more on this connection to Wigner functions? I mean, there's also this work by Jakob and so on this. Can you relate this a bit?
Yeah. So okay, I have the following 2 ideas. So one is kind of stupid. The other one is, let's say, maybe more ambitious, but more difficult, of course. So the point is, it's all a matter of frame, right? So when you see the Wigner function, you have as frame these phase space point operators, and an immediate way that one could try to tackle this problem is that now I add like one point that is associated with a noisy state. So while then the Wigner function would be, so the Wigner function, you can also see it as a minimum negativity, but it's the only actual decomposition that you can actually have, right? So in that way, if we add this noisy magic state as an additional point in the frame, so an additional, let's say, we can associate with it an additional coefficient.
Yes.
I now look for the composition of this noisy magic state. Potentially, I apply all the Cliffords. Okay. And I look for a minimization of the negativity, taking into account now the phase space point operators. Now the problem is, in that approach, it's not I think it's possible, but it's not immediate to say I mean, how if I sample a phase space point operator, how do I simulate it with a quantum computer? So maybe that's not the trivial. That's maybe non-trivial step.
I see. Okay, I see. Mhm.
Yes, but in principle,
that doesn't seem insurmountable. Let me think a bit about this, but I see
that seems insurmountable. You think? Okay. No, then the other other possible idea is that one defines a Wigner function that somehow is dependent on the noisy magic state, and you still keep the number of phase space point operators would be the same, but then let's say you would define the inner product. You wouldn't define the Hilbert-Schmidt inner product, but you would define an inner product that takes into account the reference noisy magic state. But this, I don't know if it works. I don't know.
I understand. No, I understand your ideas. I mean, that makes perfect sense, and yeah.
Because there is some similar thing in I think there is some paper on how is that called, that quantity? The divergence, Kullback, how is that called?
Kullback-Leibler?
Yes.
That's the relative entropy.
Yes, there is some inner product that is defined there that looks yes. So you define an inner product that has that is defined depending on the state, on the noisy state that you have. Yes, but again, these are all things, they're all ideas that I don't know if they can be, if they can work.
Okay.
Yeah.
Good. We can discuss this when you're visiting. That's great.
Okay, great. Yes. Yes. Okay. So in the meantime, maybe I should try to work it out a bit more. Okay. Okay.
Thanks.
Okay. So sorry. In the meantime, here it got dark.
Yeah, same here. It's like pitch dark. That's right.
Well, I mean, yeah, but here's pitch dark. For you, it seems like there's still a bit of light. Yeah, I have a question on the slide before, and it's a super vague question. So what so my impression is what this suggests is that if you have is that like starting from 2 or 3 T gates that you can realize, you already have a sort of a quantum speed up.
I mean, you should expect always. Yeah. You should, as long as you get better. In any decomposition, it's always an exponential advantage because it's the coefficient that then gets elevated to the T. The thing is here, let's say what I say is that the advantage is still quite big already for few T gates, I mean, like 300 T gates. Because like this coefficient here is much smaller than what you would get. Right. You would get classically. Yes, but one comment. But this is still actually much worse than what you would get if now T over R equal to 1, because at that point it will be 1 divided 1 minus delta squared, this coefficient, which if I remember correctly, something like 1.15, something like a bit smaller than that, maybe. Yes, so it's getting, if you have half of the resources you need, it's obviously it's much worse. Yes. Okay.
Maybe a quick technical question. I mean, the sampling complexity result is kind of lower bounded F. That's basically like a Hüfting bound, right? Technically speaking. Is that right?
Yes, it's a lower bound, yes.
Okay, good.
Yes.
Yeah, beautiful. It's really super nice.
So what this means is we also need, we should try to build really, really good T gates. T states.
Yeah. I mean, but that's the
Yeah,
that's the big overhead. And
yeah.
actually, so one thing is, so I'm reading a lot of this literature also on error mitigation in general. So there are some techniques that use somehow the fact that in NISC devices, you have the noise doesn't actually distinguish much between Clifford and non-Clifford, no? And so basically these techniques use Clifford simulations to actually compensate for the error. So it's a technique. One of the techniques is called Clifford data regression. But then there are some positive results in this direction. But then I think that then when you arrive in this regime where your stabilizer operations are ideal and the noise comes only from the noisy magic state, you can't actually use that technique because now the noise is completely biased towards the magic states. And in a sense, you're losing some possibility. Although one can also say, okay, the noise actually is coming only from this, and one can come up with tailored error mitigation techniques. Yeah.
Oh, I didn't think about this before. Yeah. These
Yeah.
error mitigation techniques are like, so good
Yeah,
for the near term.
Clifford, but the technique that is called Clifford data regression can't be applied. If you have if the noise comes from one particular kind of gate, it's useless. Although there is much work on it on NISC devices.
Maybe a bit of a stupid question. So in this last, you sort of had this division into 3 steps, right? You had this sort of classical simulation using the decomposition. You had the error mitigation techniques, and then now you have this.
You mean this slide?
No, just a general application
okay.
for the general application of this Qrom measure. So you had these 3 legs that like you showed how like this Qrom becomes interesting when you quantify how well you can classically simulate things.
Yes.
When you want to do error mitigation, and now also when you want to just use a bit of magicness to do quantum assisted simulation.
Yes.
Is there any? So in the so the first 2 parts relied sort of on the linearity of like decomposing the channels that you want to implement or the states that you want to implement into things that you can implement.
Yes.
Right? And so in this, I'm just asking, does it make sense to ask something like, say you have, maybe it's already included. Say you have less channels. So you have some target channels that you want to implement, and you have less channels than you actually need to do that. So here you have the sampling overhead for R smaller than T when R quantifies the numbers of states and T states that you have, and T quantifies the number of states that you should have. Right?
Yes.
And then I'm just like vaguely wondering whether you can do the same analogy where you ask, what does it mean if you have R channels that you do have, but you actually want to implement a unitary that's built on T channels? Or like, I don't know. Sorry, it's just a bit too vague. But
no. I think I understand it. Yeah, you can totally do it. The thing is, in a sense, I don't see, this is a kind of, if you think about how a ISK device works, you always have the same amount of operations as those that you would want. So I think in a sense, I wouldn't see where you would have the setting you're describing apart from what I discussed here, when you have limited. Well, I don't know. I mean, I don't know which other setting you would be in this situation, because I mean the reason why we analyze this is, it makes sense to consider the fact that making magic states is hard. So I consider the fact that the case in which I have less magic states than I would actually need.
Right.
So this is the motivation. So yeah, you always need a situation where making the channel is hard for some reason.
Well,
But you can totally do it. Yeah.
Mm-hmm. Yeah.
I see. Okay. Yeah. Okay. Good. Perhaps we should talk about this. But I should sleep on it and then we talk about this a bit more. But yeah, super interesting.
But I mean, the very large R limit, like R much larger than T. I mean, that's really requires new ideas. Is that so?
Yeah, I'm sorry, I didn't understand.
I mean, the case R larger than T, that requires different ideas.
Okay. Well, first of all, the first thing that one has to solve is what do I actually decompose? Because so what is my target state? Shall I target as a state like the T times the zero state or someone, I don't know. There is a bit of arbitrariness there, but actually, I mean, it's still a convex optimization problem, and I can set it up like one can set it up. It's a bit. I think it's not so clear how to formalize it properly, I would say. I think there is more of that problem.
I see. So there's not only a technical problem, but also a conceptual one.
Yeah, a bit of a conceptual one, because if you think about it, potentially, you can also include magic state distillation in the definition. So I think I think, anyway, we thought about it for a long time, like characterizing the set of all states, like this state, so this set here, characterizing the set of all states that can be reached from a resource state by stabilized operation. This is, I don't know, it's very tough problem in general.
Yeah, totally. I understand. Good. No, there's a lot to talk about. When you visit, I'm looking forward to this a lot.
Okay. Yeah. Well, also recently there were these works really on characterizing the states that can be reached from a stabilizer operation. So yeah,
of course. In fact, I had a discussion on this earlier today. Yeah, indeed.
Okay.
What's the knowledge in that part? I mean, it's a bit out of scope of your talk, but I find it quite interesting to because as I thought, like if you think of all the possible states, some weird manifold, that like you just need some some significantly smaller subset of states from which you can then sort of start out, and under the Clifford orbit, you kind of reach your whole state space quite fast. But I mean, that's just an intuition based on random circuit ideas. But I mean, this has not directly, cannot be directly applied to this setting. So what's the, what does one know about this?
Well, I don't know. I don't know if I can answer the question. I don't know. I think maybe the most general question is like, if I have certain amount of these noisy T states, so R noisy T states with R larger than what would be needed, what's the minimum amount so that you can actually decompose the ideal T states that are fewer in terms of the noisy one? Maybe there is a maybe there is a threshold in this question. I think there is. Yes, but I don't know. But there are possible questions that one can ask starting from this.
Wonderful.
So if there are no, are there more questions? If there are no questions, I think we've been going on for quite a while.
Yes.
So I think it's okay.
Yes. Thanks so much again for this wonderful talk. That was super exciting. Thank you very much indeed.
Yes.
I also apologize for my
thanks.
technical lapses. I will glue the parts together, and that should be easy. And I'm really looking forward to the visit.
Okay. Yes. Thanks a lot. Thanks for all the questions. Yeah.
Good. Wonderful.
Bye bye.
Thank you very much.
Okay. Thanks a lot.
And
Thanks.
have a nice Christmas.
Thank you.
Yeah. Bye bye.
You too. You too. Bye.
Thank you.